hopefully you can all hear me okay today. If you can let me know in the chat if there's any questions or any issues with the sound, but hopefully you can all hear me. So my name's Adam Taylor, and I run a small company called Adiuvo Engineering and Training, as you may or may not know. And today we're going to take a look at the introduction to AMD Vivado. It's been a while since we've done this. I think the last time we did this was way back in 2020. You know, we've moved off. We've looked at Vitus HLS, and a few other exciting things. So it's good, I think, to go back to the basics and catch up on what has been evolving in Vivado over the time. So, like I say, if someone could just let me know that you can hear me okay, that would be grand. The slides, everything's been recorded, and it will be available after. If you want any of the slides or anything for this, all of the slides and the source code that we're going to do this are available at the GitHub link just down there. So how we're going to do this today is I have a few slides to introduce a few concepts to you and talk about a few aspects of Vivado, and then we're going to jump in and we're going to look at a couple of labs. The labs are going to be fairly straightforward. You know, I'm giving you the RTL for it. So what we're going to do is we're going to kind of work through the standard sort of project creation, simulation, synthesis, that kind of things. We're then going to move on into sort of IP Integrator and looking at what goes off with IP Integrator. And if I've done it correctly, then we're going to inject some timing issues, and we're then going to be able to see how we can find that timing issue and correct that timing issue in Vivado. Now, I'm trying a slightly different approach today to what I normally try. So I've actually got a remote machine running that we're going to log into to see Vivado on that. And that's because I'm hoping that will give us a nice resolution with the screen and everything for sharing over the video. So hopefully we'll be good to do that. So I'm going to make a start now as we start talking through our slides. And I want to really talk about a little bit up front about where this all fits in the AMD framework. You might have been to previous sessions of mine where we've talked about Vitus AI and Vitus, which allow us to sort of accelerate sort of, well, Vitus AI enables us to create machine learning inferences on MPSoC type devices and ACAP devices. We've done some sessions on Vitus where we can look at using sort of the embedded and the accelerated software to flow. I guess the most recent one that we've looked at there was the Microblaze class, where we use that quite a lot. And then, of course, we have PETA Linux. We ran through a PETA Linux lab just last year, and then we've got Pink and AMD Vitus and Vivado HLS, which we ran through, where we looked at how to do high level synthesis. We've also got, of course, what we're looking at today, which is Vivado, which gives us that ability to do the design capture and implementation for a base platform, and that's really what we're going to be looking at and focusing on today. So to give us a bit of an overview, if you're not familiar with it, you know, Vivado it's the foundation of all the designs and the higher level tools. It enables us to capture designs using VHDL or Verilog. We can also import IP into the large IP library, and we can do that as well if you've seen the webinars that we did, the workshops that we did on Vitus HLS. You can pull those HLS IP codes into Vivado as well, which gives us a nice ability to capture our base design. What's really nice about Vivado actually is that it is a very enclosed environment, in that we can run through and take a look at the simulation. You know, we can capture our design in there. We can create our design if we want to. We can simulate it using Vivado Simulator. We can do the place and route and the implementation, and then we can also take a look at things such as generating power estimations and doing advanced things with the design as we go through it. We can also create the higher level aspects of this. So if we want to go away and create our own acceleration platform or something, our own platform for our custom Vitus AI on one of our custom design boards, you know, we're going to be starting out in Vivado. So it's really the important basis for everything that we are going to be doing. One thing I should say is, if we go through this, if you want to ask any questions, please put them in the chat and I will try to answer them as we go through. There'll be some times when things are building and we can take a look at that. So I'm going to assume that most people are quite familiar with this, but the steps that we go through in Vivado to implement our design are, we will run through doing the synthesis, where we translate the HDL design into a series of logic equations that can be mapped into the resources that are available in our target FPGA. Once we've got those, that synthesis completed, we've got those resources mapped into the FPGA target devices. Our tool then goes through the placing, where we place the elements of our in the basic logic elements of the FPGA design of the FPGA. So it places them physically in the FPGA at certain locations, and we'll see this later on when we come to looking at some timing analysis work and some timing closure. Once we've got all those elements placed in the logic, then they need to be routed and connected together as we will, as our design requires them. So we'll then run through the routing, which will connect through the interconnect and place it in there. Now, crucially, what we're going to see is that routing and that placement is really critical for getting the timing performance, as you would expect, that we will see out of our FPGA. We also have then, obviously, we then have the final bit file generation, which allows us to run through and to create that programming file that we can use on our design. Now, as we flow through this, as we go through this, we're going to be using constraints to control the implementation flow, or to instruct the implementation flow what we want to do as we go through it. And that's where the XDC files come in. And as we go through the lab examples today, we'll be using those constraints to define basic things such as IO placement and things such as timing constraints and such like, so we know what we want to do with them. Now, if we take a look at IP Integrator, this is really the core at the heart of Vivado for capturing a lot of our designs. And it gives us the ability to graphically capture the system level design. So if we're working with, say, for example, a Zinc or Zinc MPSoC or an ACAP or Microblaze, it really gives us a nice ability to create the design, the plug and play design. So we can pull in, as you'll see once we start in the labs, you can pull in the IP, we can connect them together, and we can start working quite easily. So if you followed my blogs and projects over the years, you'll have seen that we've used this to create things such as, video processing, audio processing, pipelines and stuff like that, because it's relatively easy, it's really quick to do. There's a lot of automation in there. There's a lot of automation that can be very, very powerful and useful. And it can, in a lot of cases, if we're working with development boards, it will be very board aware, so we know what we're doing there. Like I was just saying, it's quite intelligent, so it gives us a nice hierarchical system view. If we want to, we can create hierarchical blocks, and that's really important if we do more advanced things, such as working with partial reconfiguration, for example. We also can have the live design rule checking, so it can really simply check our interfaces for us and check that we're working, that we've connected it up properly. And it can also do quite a lot of the heavy lifting, because it can do a lot of connecting of AXI interconnectors, configuring of processors and IP blocks as we want and we desire. And like I say, there's a lot of board awareness built in for the development board, so it makes it really easy to get to grips with that and start working with that. Like I was just saying, as you'll see as we go through in some of these instances, you'll see that we get what's called the connection automation, and that allows us to automate some of the heavy lifting that Vivado might otherwise have when we want to connect blocks and modules together with each other. So let's just take a quick look before we do that. My machine's locked. We can take a quick look at Vivado. And the visual tool that it is. It's a relatively simple nice, easy to use. If we open up, actually, if we open up the second project for the time being, I'll just quickly show you what it looks like in reality. We can see that we've got a nice clean workspace. And when we work with IP Integrator, if I pop this out for a second, you can see it's very visual, very easy to work with. Is this looking okay on everybody's screens? Can everybody see this? Okay, I think this looks quite nice. And then we've got of course, we've got all of the IP that we want to be able to add in to our design and create it from there. So it's a really nice, really flexible way of doing it. There's a couple of things as we go through this, though. A couple of techniques, a couple of processes that I want to talk about before we get too far into the process, because the tool's actually quite good at telling us what we want to do or what we want to know, and it's very good at giving us information up front. So if we're doing a large design, it's very good at giving us information up front that's going to help us know whether our design is going to run or not, or whether it's going to be successful or not. And one of the things that we can often hit with designs, and we're not going to look too much at it today, but one of the things we can often hit with designs is clock domain crossing examples. So years ago, when I started being an engineer, I was told, you know, the ideal solution for the projects that I was working on was that we would use one clock, and that would be all that was in the design. Now, unfortunately, as we've moved into these very complex designs, very capable FPGA architectures, we tend to find that we're moving away from just being able to have a single clock. And we move, as we look at the results of the Wilson Group survey here, we see that we find that we end up in a 2 to 4 clock domain systems for most of our designs. And if you think about that, that makes sense, because if we have a processor in there, we may have we might have a processor clock running that does some low speed AXI transactions and configures the IP cores in the programmable logic. But we might have a processing path as well, which is running much faster. And then we may have, of course, inputs which are running in different clock domains, and outputs which are running in different clock domains. So we need to think about how we safely transfer data between those clock domains without getting any corruption. And this is one of the things that actually Vivado is quite nice at helping us with and showing us how to do. If we go over to this screen, so the issue, like obviously as engineers, we all know, or hopefully we all know, that with clock domain crossing, if we get it wrong, then we can get metastability occurring in our design, which will lead to corruption of the signal or corruptions of the data, and incorrect behavior as it goes downstream. Maybe our state machine locks up, maybe we get the wrong value of a calculation coming out somewhere. And what happens that causes this metastability is that when the flip-flop setup or hold time is violated, we get these timing issues. And we're going to see this today in the lab, not necessarily just from the metastability, but from the actual timing violations as well that we get due to how we place and route them. So somebody's just asked a great question, and I'll come back to that in a minute if you don't mind, and we'll talk about that in a second or two. So if you've never seen this before, this is quite cool as to what happens. You know, we have our register here with a setup and hold time in relation to the clock. As long as the data on the input stays the same for both the setup and the hold time, then after the propagation delay, we will get that passing through to the output. Now, if we were to change that input during either the setup or the hold time, what happens is the behavior of the flip-flop becomes metastable. It goes through state, as you can see in that image over to the right there. That is what's called metastable. It's neither 0 nor 1. It goes into a state in between. Now, it will recover from that state. but it's going to go either to a 1 or a 0, and it depends, and that just depends upon the recovery mechanism of the flip-flop. It's a little bit random, and that's why it can lead to corruption of data. So we need to very carefully think about clock domain crossing and metastability in our designs. Thankfully, though, Vivado helps us a lot with this and gives us a lot of help with this in what are called the XDC macros, and these enable us to be able to do safe transitions and safe clock domain crossings from one clock domain to the other. So we get the basic two-stage synchronizer, which enables the time for the flip-flop to recover from the metastability event. We get gray code synchronizers, handshake synchronizers, pulse synchronizers, and of course the asynchronous FIFO, which allows us to move from one clock domain to the other for high bursts and throughputs of data. So these are really important, and I'll show you in a second in Vivado just where they are actually, because if you've never come across them before, it's quite easy to pick them up in the code and run through them. We also have the synchronous, we also want to make sure that we're doing nice, sensible things with our resets. So there's synchronous and asynchronous resets provided there. Like I was saying, to do this within the AMD ecosystem, we want to use the Xilinx parameterized macros. And these will give us nice CDC structures. And depending upon whether you're using 7 series or ultra scale architectures, the user guides are either 953 or 974. There's a very nice and easy way, just coming back to Vivado for a second, there's a very nice and easy way to actually find these. If you want to put them, you can put them in IP Integrator. But if you open up the Vivado standalone code editor, and under the language templates, and we'll go under VHDL because I'm a VHDL person. You can find the XPM CDC, so all of the XPM CDCs, the FIFO, so all of the coding structures needed that you can copy and paste into your design to help you get going with it. Just down there, there's just a little example of a simple sort of passing a reset from one clock domain to the other. So these are very important. One of the nice things about this, though, is that we should be, CDC is an architectural thing. We should be planning and thinking about this when we do our designs, when we do our architectures. But Vivado will give us a nice CDC report. So if we have any issues in our design or potential issues in our design, once we've actually run synthesis, we don't have to go through and do place and route and implementation. So once we've done synthesis, we can actually take a look at running the tickle command report CDC, and we will get a CDC report in our tickle window that will tell us if we have any issues. For example, here you can see that it's found a synchronizer which we've created using the CDC. And it's also found some unsynchronized CDCs as well, which you might want to go and take a look at. And then similarly down the bottom, there's a lot more information on what's going off and where we might have some CDC type issues. So this is very, very important for doing that design. The other element of the tool that we can see as well, if we want to, is we can get a clock interaction report, which is quite nice, and it will show you all the clocks in the design. And it will show you their interactions as a grid to show you whether they're timed, whether there's partial false path or something in between them, and that can be really, really useful when you're thinking about your clocking structures, your clocking architectures, and verifying your design within Vivado. It also means that we will need to create some clock constraints and some false paths, and you'll see how to do that as we move into the lab sort of element. If you find this, if you find an interclock path, so say you forget to do your CDC, say you forget to do the report CDC, once you've done synthesis, you run it all the way through to the end. You've got a nice fast build machine, and it only takes a few minutes. You get to the end, and you'll see that you have some inter-clock path issues. So you'll see there are some inter-clock path issues. So this is telling you there's an issue between the clocks that you've got on your design. We could follow this through. You're looking at the detailed report, and we'll see this a little bit in the labs coming up. But you can follow this through, and you can probe this through to the actual schematic level side of it, where you can actually see what's going off and what you've got. So you can see here the two clocks here, the signal passing here without doing any clock domain crossing or anything like that on it. Which I think is really nice. It's really visual, and it really helps you get through this. So a couple of the other things I want to talk about before we delve into too much, because we're gonna walk through the basics in this tutorial and show how to do everything. But one of the key things I want to kind of run through is some of perhaps the things that might be of use to you that you're going to come across later on as well, that will help you benefit. So we're going to take a look at the strategies and reports as well that we can get out of the tool quickly before we jump into the fun side of it all. Now, strategies are great because strategies are defined in Vivado as they're an implementation feature that allows us to control the implementation results that we're getting out of there. So we can see perhaps if we're having issues with our design, we can perhaps take a look at running strategies to explore the timing performance. Or if the design's reporting that we have congestion, we can take a look at running through strategies where we might be able to look at strategies that would reduce routing congestion in areas of the design. Maybe we want to optimize for area because we've got a small design, or we want to optimize for power because we're in a very power constrained environment. Or maybe we just want to do a quick look-see, in which case the quick flow can be quite useful. So the strategies are really nice and useful for allowing you to get through and try to find out why your design's not meeting timing enclosure, or what you can do to help configure it for doing things such as timing or power. And we'll come back to these strategies in a second as we go on, because one of the important things that we can get out of the tool as well, is that we can get reports which can be used to help us focus on performance issues in the design and see whether our design is going to work or not. So we can see that we've got the design analysis reports that will come out, and that'll help us and talk to us about providing information on design timing, on congestion, and the complexity of the design. It'll also give us some nice scores as well, as to tell us whether our design is likely to implement and likely to meet timing, which is really important. And we also have quality of results reports as well, which provide overall design assessments and methodology assessment. And it can actually also make suggestions to fix issues in our design. Some of these suggestions you have to go away and implement. Some of these can be implemented automatically in the tool to make it work. So that's one of the key things that we can do with these reports and with these elements. So with that, let's take a little bit more of a look in detail into these things. So in the design analysis report, we can get that pretty much after we've run the optimization stage of the flow of the project. So we can see that after we've run the optimization stage of implementation. So we need to have run the synthesis and that initial optimization, and then we can get the result to provide us information on timing, on complexity, and on what it thinks the congestion is going to be. Now, these things are really important because as engineers, the earlier we know something, obviously, the easier, the quicker, the better it is to be able to fix and implement. So if we can find out early on that we might have issues with our FPGA implementation, we can fix them, as opposed to having to spend 3-4 hours waiting on place and routing only to find out that there's an issue and we need to go away and take a look at it. So one of the things that we can do, so the design analysis report is also going to give us some information on the complexity of our design, and that is the design risk for implementation. Obviously, we want a design that we think is going to implement nice and easy and is going to give us a nice timing closure. So we can see from running through the design, we'll get some metrics out of it. So we'll get a rent analysis, we'll get a fan out, an average fan out, and we can say that if our average fan out is less than 4, and our rent analysis is less than 0.65, we've got a fairly low risk design, and we should be able to achieve the timing closures and the performance that we want. If we're between 0.65 and 0.85, and our fan out's between 4 and 5 on the average fan out, then we might have some difficulty in placing this design and getting it implemented without facing some congestion or some other issues in the design that we'll have to address as we go forward. Now that's the design analysis report. The other thing to take a look at is the quality of results and the quality of result suggestions that come out. And again, we can run this just after we've done the optimization. So it's a good thing to do and to run through after you've done that optimization. One of the key things that this is going to give us, which is really quite nice, is it's going to give us a score. And I really like this because when we do a lot of consulting for clients, it's one of the first things we ask our clients to do is kind of go away and sort of run this on their design if they're hitting issues, because it'll give you the score as to what Vivado thinks it can do with your design and with your implementation. So we could take a look at, if the score is 1 or 2, then if it's 1, it's going to cause us issues implementing. If it's 2, it will probably implement, but we're going to have some timing issues. So we need to look at constraints and how we've written the RTL and the HLS. If it's a 3, then we're bordering on the verge of success. It might work, it might not work, but we might need to look at those strategies that we were talking about earlier on. We might need to review our constraints and so on. But if we're in the 4 or 5 area, then we have a reasonable confidence that our design is going to implement, and we can implement it using with a few timing directives or without them, depending upon what the tool says and what the score says. So that's really important because it gives us a good way to be able to understand the risk that's associated with our design as to whether it's going to implement or not. And if you take a look here, is a simple example for a design that comes out. It gives us some scores. It gives us some suggestions and such like to go away and implement. So you can see here it's telling us fix unsafe paths by amending the design or adding false paths and data paths. So basically, it's taking a look at our design and it's saying, go away, please, and take a look at the timing constraints that you're working with, and make sure that they are sensible timing constraints in the design. So far on our quick introduction to Vivado, we've looked at what Vivado is. We've looked at one of the interesting things about clock domain crossing. We've looked at the results that we can get out of it. The last thing we look at before we jump into looking at the labs is going to be how we can reduce runtime in our designs, because this can be quite a significant pain. Could be a very significant pain point. So AMD Vivado, it uses a physical design database called design checkpoints, and that's where it stores the placement and the routing. So these design checkpoints allow us to save and restore the database at key points in the design flow. So not only can we save and restore them, we can also use them as guidance for the next stage when it comes around. So we can see so we don't have to, or the tool correctly doesn't have to spend so much time running through it and going from scratch. And we'll come back to these DCPs in a little while, because there's something else that we can do as well when it comes to running the synthesis. So it can take a while to run through the FPGA implementations. The example I've got today, you know, we're running on our build machine, so it takes maybe a minute or two in between each run, but that's not representative, obviously, of a real design where it could take quite a long time. So when it comes to synthesis, we have a couple of options. We can ask it to perform global synthesis, which is a traditional, what you might understand it, you know, traditional top-down synthesis from the top-level module, and it goes all the way through all the modules in the design. And if we select that option, then it's going to take a long time, because anytime anything changes in the hierarchy, we just change an AND gate to an OR gate or something, all of that has to be rerun. So it takes, every time we make a change, it runs through. What we can do, and the thing that we'll be doing by default, is we can run what's called out of context per IP. And that allows us to run synthesis and creates a design checkpoint for every IP block in our design or every module in our design. And then these are then collected together as black boxes at the top level of the implementation. And that means that if we change one of these modules, only that module needs to be resynthesized, and it's just stitched into the rest of it when it's run through. So it gives us so the first time we run through this, it takes a reasonable amount of time, but after that, it's much quicker on the iterative flow, because we're changing things ever so slightly. We also have the like the out of context per IP. As you'll see, we'll be doing some work with block diagrams, and we have the ability to do out of context per block diagram as well. So that just allows us to work on a larger scale granularity there with that. So we can do along with the out of context and the out of context per block diagram, we can also do incremental synthesis, which we can set in the settings. And this, we can point it to the previous design checkpoint. It'll automatically, if we turn it on, it'll automatically use the previous design checkpoint. But if we want to, if we've saved one for a particular reason, then it can use that defined checkpoint also. And similar to when it comes to doing the place and route, we can do the exact same thing. We can set the incremental implementation, and it will run through. And what's interesting, as it runs through, it will give you a report of how much of that design checkpoint was reused as it's going through the recompilation and the reimplementation. You'll see that drop out in your Tickle console as to what it is, as to how much it managed to reuse or not, as the case may be. So that's all of the sort of the intro, the backgrounds, and everything that I wanted to share with you. What I want to do now is I want to start taking a look at some of the labs that we've created for today and show you some of the capabilities of Vivado. So in the best Blue Peter tradition, I've got 3 that we've already created, but we're going to go from scratch again. But I want to come back and answer Roy's question at this time, just before we go on, where he was asking what kind of tests are done when Vivado creates a simulation without writing a proper test bench architecture manually. And I think the real important point for this one is that you're going to have to write the test bench, and you're going to have to run it. I'll show you in the simulation window itself in Vivado Simulator. You can do simple things like you can set up clocks and force signals up and down and such like. But realistically, you need to write a very simple test bench. And there's a few things in there that Vivado's got to quite help you with. And as somebody was else asking, is it good to make AXI IP by writing our own rather than using Xilinx IP? And it all depends how you want to use your IP. I'm a big believer in that our jobs as engineers is to create the product that meets the solutions, such that it meets time, such that it meets quality, schedule, and time, such that we can ship the projects. So if there's an IP in the IP library that works and you can use it, then I would say use it. If you have to go from scratch and write your own AXI IP, then I think that's a point as engineers. And as someone who's just asking, will we be taking a look at DCPs? We'll touch on them briefly. It's not something that's hugely integrated as part of these labs, but we will come to it and touch on it a little bit. So I'm going to get started with the first lab, and I'm going to create the first project. So Carlos, that's an interesting question. So is the report CDC in Vivado comparable to commercial CDC analysis tools? And it's a little bit of sort of half of one, half a dozen of the other. The commercial CDC tools allow you generally to find it from the RTL, not from having to have done synthesis and such like first. And they can be a little bit more IP. They can be a little bit more IP centric. So you can take whichever one you want. Jesus, you were saying you can use Xilinx IP in products that you will commercialize. Yes, you can. You can use them in products that you commercialize as well. So we're going to take a start with this. We're going to come over here. I'm going to call this Viv1 Live. Hopefully I've not got another project called that. We're going to walk through simple project creation steps, and we're going to add the files that are in our that are in the GitHub repo that I've shared. That the links at the top of the option, and it is a simple block average and a simple test bench for that. Obviously, I don't want the test bench to be synthesizable, so I'm just going to tell it that we're doing this for simulation only. We're not going to add any constraints in at this point in time. And in terms of boards, I'm going to pick the Digilent RTZ720. If it's not installed, you might need to just install it and click on it to install it. But that's the board I'm going to use, primarily because I know that's going to give me the timing issues that I want on this for these labs. So I'm going to click on next at that point, and we're going to click on finish. So while that's opening, so Atar, you were saying, can we use version control systems for Vivado projects? And yes, we can. We just have to be careful about what we want to version control. And it's a little bit more complicated than what I could perhaps explain here. So what I'll do is, if you don't mind, I'll take that under advisement and I'll create a blog about showing how to do it, because we can source control the VHDL or Verilog, the XDC constraints and things like that. But there are other aspects of the Vivado project that you might want to use and put under config control. So I'll create a blog in a couple of weeks and show how we can do that. So someone is just asking, does more LUTs in the logic degrade the logic speed? And that depends on the number. It really depends on the number of LUTs you have between the registers. So that will have a big impact. The more logic you have between register points, that will degrade your speed. And you'll see this in the lab coming up in a minute, in the second lab, that's quite important really to understand where those registers are and what we put in there and what we place on there. So now you can see I've opened this project. We've got a simple average RTL block here. I've got my test bench here, and if I double click on them here, we can get the code opened in the editor. And you'll see that we've got the average, a simple test bench here. We're just doing a very simple one here. You know, we're just applying a number of values to it, and then we're just applying that to the unit under test. Karthik, yes, I will. I'll do a blog on version control packaging of custom IP as well for you as well. Yeah. Similarly, the block itself, the IP block itself that we're going to simulate and test and make the center of this project as we go through, it's just a simple rolling average, a little bit of simple maths in there. Its functionality is not too important. It's there just to teach you the basics of it. So if you've created this, you know, the first step as professional engineers, as we're going through this, you know, the first step is to begin to actually simulate the design and make sure the design works properly. So what we're going to do is we're going to run this simulation. We're going to run a behavioral simulation. So we're not going to apply anything. We're going to by behavioral, we mean we're running the RTL that we've written. So we're not running the results of the synthesis. We're not running the results of the place and route. We're just running the results of the RTL that we've handwritten. And you'll see it runs through quite quickly. And actually, because Vivado Simulator has a little setting where it runs through a set period of time initially, you'll see that it runs through and it runs to completion. And if I pop this out here, this untitled one window, you'll see that this is our this is the top level view of the test bench. So this is the test bench with looking into the ports of our module. One of the things though, it's all in hexadecimal. So we're going to change the radix to unsigned decimal. And you'll have to trust me on this. But the values are correct for an average of 118 and 196 when it pops out. Now, like I said, this is just the top level of the FPGA design because we're just looking at what's in the test bench here. We might want to look at what's in the actual unit under test a little bit more in detail. So we can select the unit under test. If I make this slightly larger, we can select that and we can add it to the wave window. And you'll see once we've added it to the wave window, there's a lot of information that's missing because it wasn't, to make the simulation run faster, it wasn't logged when that simulation was run. So it wasn't stored to the log file. So if we restart our simulation and then run our simulation again to run to the end of our time period, what we get this time is we can see exactly what's going off within our HDL, within our RTL that we've written. Again, it's all currently showing values in hex, so we can save the hex values. We can change the hex values again to unsigned decimal, and we can see the results of the output results as we go through the fixed point multiplication and running through that. Karthik, your question about going to a third-party simulator, I'll come back to at the end and answer if you don't mind. To give us this little bit of, it can be a little bit difficult to see what's going off where. So one of the better things to do is to include a divider if you add in these elements. So we can call that UUT. Such that we can divide our design and we can see where is the top level and what's the lower level unit of our design, and it stops it making it difficult. So the question that's coming about debug CDC crossing in simulations, it's actually very difficult to debug CDC in simulations because it requires you to do a timing simulation with all of the timing information put in there, which makes the simulation take a long time. But it also requires that because you don't know what the clocks are going to start up like because the two clock domains are completely asynchronous to each other. It requires that you find that sweet spot, shall we say, in simulation that causes the metastability effect to occur. So it's very difficult to find CDCs in simulation. So it's much better to use the method I've showed you earlier on, which is using the tool's capabilities to report the CDC and find it, because it's very difficult, like I say, in simulation to find it. Once we've done that, once we're happy with the simulation, we're going to close the simulator for the time being. We're going to discard anything that we've put in the waveform, and then we're going to run the synthesis on this. So we're just going to run the synthesis for the first element of it, and hopefully it shouldn't take too long on this machine. On my desktop, it was taking a minute or two. On Colossus, it shouldn't take too long. So if anybody knows the name where Colossus comes from, feel free to put it in the chat. We've been trying to name our build computers after historical computers. So we have Colossus, the Bomber, and a few others. Once synthesis is complete, what we're going to do is we're going to open the synthesized design. And what we're going to do now is we're going to look at assigning the I/O in the design. So the first thing we're going to do with this I/O tab down here is we are going to set these to LV CMOS. We're not going to leave these as default. I've made this mistake before. We're gonna run this as LV CMOS, and we're going to open the scaler port. We're going to find the clock. The clock's the really important one. We're going to change these last few down here to LV CMOS also, but the clock is the very important one because that's the one we don't want to auto place because it's a clock. So we're going to put this on pin L16, I believe. And I'm just going to double check that in my instructions that is the right pin to put it on. I believe it is. I've only done it 5 times today already to make sure, you know, but now I'm beginning to doubt myself. L16, it is indeed. Once we've got that on L16, we can go into our tools, we can go into IO planning, and we can tell it to auto place the ports. I'm going to tell it that we want to place all of them. And then we're going to say, actually, apart from the one that I've just placed, I'd like to automatically place them all, please. And then I'm going to click on finish. And you should see that now all of these have a placement, a pin in them now. We're going to save this. And this is going to get saved into, it's going to ask us what to save it into, and we're going to save it into an XDC file. And I'm going to call this io.xdc for the inputs and outputs. And then on our files, if we look in our files, maybe I can make this a little bit bigger if I drop that down a little bit. Peter, did your screen start catching up, or has anybody else had issues? Or we'll see that under our constraints here, we will see the constraints have been added in. So you'll see the signal types, the IO types, and we'll see the pin package. So yeah, the ILA design is really quite impressive. And the way I tend to put it in, you can put it in through the synthesized design, but the way I tend to put it in is to put it in via the block diagram, and I'll show you how to do that in a minute on the next one if people are interested in seeing that as well. So we've now got our IO constraints, we've got our design, we've got everything we want. If we run through the implementation now, this should hopefully run through quite quickly. It's quite a beast of a machine, so hopefully it should run through quite quickly. If there's any other questions while you're talking, just feel free to pop them in. I also added a poll. I don't know if anybody's seen that. Just out of curiosity, if you want to try and take a look at that, that would be wonderful. Synthesis is complete, and I wanted to run it. Oh, it's doing it already. It's running the implementation. It lulls you into a false sense of security with how fast it is at doing these simple-ish designs. So there's a couple of questions just coming while that's running. So one of them is why most of the time the synthesis design cuts the logic as compared to what you see in the elaborated design. So that must be then in your case that the synthesis tool is making some optimizations. So it's worthwhile taking a look at your RTL to see what's going off in there, to see what it's reporting on, and read the reports as well to see why it's what it's reporting on as it's optimizing out. Zahid, is there a way to make it run for implementations faster? It's slow for even small designs. The fastest way, I'm afraid, really is to use these sort of the settings for the incremental implementation and such like. If you want, you could go for a very quick example. If you wanted, you could go with the quick flow strategy. And that will run you through, that will run the script, the flow through in a quicker pace, but you might not get the results that you expected. So Jamie, you're saying what memory would you recommend for Vivado? 32 gigabytes. So we run all our machines. All of our machines generally have about 32 gigabytes of DDR in them. The machine that you're seeing at the moment that we're building this on's got 32 gigabytes of DDR5 in it. Our laptops that we use have 32 gigabytes in it as well. We have one laptop that's got 64, and I've not really seen much difference, to be honest, in performance. So once we've got that, we've now run through a very simple flow where we've created a project, we've added some RTL, we've seen how to create a simple simulation, we've seen how to add I/O, and then we've generated and implemented the target. So it's a very simple project. So someone just asked a great question: what are the major limitations with respect to running on Vivado on Windows versus running on Linux? To be honest, we have both. We have some Linux build machines as well that we use for things like, particularly when we're working with Pedal Linux or with Vitus AI or with the Vitus accelerated flow, we tend to be on Linux. Linux is probably a little faster in terms of implementation than Windows, but we also seem to spend, as all engineers do, an awful lot of time writing documents and doing PowerPoints and things like that, which we find easier on our Windows laptops. Hence, all of our laptops have Windows on it. So there's not a huge difference, to be honest, between one and the other. So with this, what we're going to do now is I'm going to save this project as another project. Save as. We'll call this Viv2 Live. And there we go. It runs through and it shows this. So what we're going to do here is I want to show you a little bit about how we can work with IP Integrator and pull our own designs and stuff into IP Integrator. So what we're going to do now is, for the first time, the first project that we looked at was all RTL. So it was RTL that we'd written, we'd simulated, we'd worked with. What we're going to do now is we're going to create a block design, and we're going to start working with Vivado IP Integrator. So we're just going to let it open the block design. Once it's opened the block design, we're going to see this over here, and I'm going to pop this out for a minute and make it flow, because otherwise it might be a little small. What we're going to do is we're going to add a simple IP first from the IP library. So we're going to click this plus button, and we're going to come over here and we're going to add a FIFO. Every engineer loves FIFOs, don't they? So we're going to add a FIFO generator onto the design, and we're going to see that we're going to get this automation connection running up. I'll click on it, but I'm not going to do anything with it, because you can see it's already saying, you know, you've got clock in. I know what the clock interfaces are on this board. Would you like me to set your new clock wizard up for it and do some connections and everything for you? In this case, I don't, but I just wanted to show that just to show how helpful Vivado can be. What I'm going to do is I'm just going to go back to the first screen for the time being, and then I'm going to click on the sources tab, and I'm going to find the average block. So this is the RTL block that we've written. And I'm going to right click on it. And I'm going to say add module to block design. And then hopefully when I go back to the block design, I'm going to have two blocks on there. Now I've got the FIFO generator and the RTL block that we previously wrote. So Kenny, that's a good question. Is the FIFO same as BRAM? So the FIFO the FIFO might use BRAM, or it might use inbuilt FIFOs. But the FIFO is basically just, there's no address channel to it. It's just data that gets written into it, and then data gets pulled out of it. So it's essentially a first in, first out. That's what FIFO stands for, first in, first out memory. So as we write data into it, the data is going to come out. And what we're going to do is we're just going to set this up very simply, that our external connections on the FPGA, we're going to set this up so the external connections on our interface, on our FPGA, are supplying the FIFO. So, Maximilian, you say, is it just for CDC interfacing? And it doesn't have to be just for CDC interfacing. You can use them as buffers. You know, if you've got data flowing from one block to the other, And so you've got a producer and a consumer block, and you don't want the consumer block to slow down the producer block. You could put a FIFO in between to act as a bit of a buffer, an elastic buffer. So FIFOs are really quite useful features in our FPGA world. So what you're asking, is there an IP for double buffer? There is. I want to say there is now. So if I do XPM, so you'll see now we get this XPM CDC dropped up. I'm not going to put this in our design, but if we double click on it, you'll see that we get a list of options that you can implement the type of CDC crossing that you want to implement in there. I'm going to remove that from our design, but I'm just going to remove that from the design, by the way, there. And I'm going to close that. Okay, so once we've got this, I'm going to double click a little bit. Yes, Ismet, yeah, the recording will be available. If you look on my website or come back to this link, you'll be able to find an online recording of this, and all the slides will be available. So I'm going to come back to this recustomize the FIFO. So by double clicking on it, we can recustomize the FIFO. We're going to leave it as it is. We're going to leave it as a common clock block RAM. So there's just one common clock to it. We're going to go to the ports, and we're going to change the port width to be 8. And hopefully that should ripple through to the read and the write. They're now both 8 bits. Importantly, we're going to leave this output registers unticked just to show the example. We're going to untick the reset pin because I don't want a reset pin. And then we're going to look at the summary. So we can see here that we're using a block RAM. Read and write ports have got the same clock. We've got 8 bits on the input and output, and we've got 1 kilobyte of depth essentially. And here we've got a read latency of 1 clock essentially from when we want it. What we're going to do now then is we're going to connect this up in our system. So we're going to connect the clock and the reset, and we're going to make those external as well. So we're going to say they come from external to the FPGA, just like the write input does. So just like the data in, and the write enable signals do. We're going to have the same clock, obviously, because we're running in 1 clock domain in this example. And then for the FIFO read, we're going to connect the FIFO read to this. So we're going to connect the empty signal to the read here. Oh no, I've gone wrong. We're going to connect the read to the read enable there. And that's a good example of where Vivado is very aware of what you're trying to do, because I tried then to connect the empty signal to the read, and it said no, you can't do that because you're trying to connect an output to an output, which is quite nice. It can save you a lot of bugs and issues. We're going to connect the empty signals there. We're going to connect the data that comes out of there with that, and then these 2 final bits. We're going to say this FPGA is going to make these and push these external to the external world. And then we're going to hit this button to redesign it a little bit. We're going to smooth out the joggles. And you see we've got the data comes into the FIFO, so it's coming in from the external world into the FIFO, and then our average block's calculating the average, and it's just throwing out the result. Very, very simple solution. Now we're talking about ILAs and in-chip ILAs, and if you want to use in-chip ILAs, so we can use ILAs by clicking on the Add IP here, and if we type on ILA, you'll notice we get 2 elements. We get a system ILA. So a system ILA is really good if you want to work with like AXI and you want to see what's happening in the AXI transactions. The system ILA will show you sort of AXI read, AXI write. It'll tell you exactly what's going off, as opposed to just presenting you with the waveforms to decode. Because we would be looking in this instance at a fairly simple solution, we can put in a normal ILA, and the normal ILAs, they come with the ability to look at AXI and such like as well. Oh, meant to double click on that module. So they can come with, they can take a look at, they can monitor AXI, and they can monitor AXI 4, AXI Lite, AXI 3, AXI Stream. In this case, though, we would want it to just monitor native logic signals. So we might want it to take a look at, say, for example, standard logic signals that are coming out of the FIFO. So let's try this with sort of, if we have read and empty, so say 2 signals, say there. Oops, I've done that wrong. Number of probes should be 2. And that should be 1. So we would then connect the clock to the clock that we want to sample it on. We would connect that, say, to empty, and that there to read enable. Now, when I did my example earlier on, I actually didn't include the ILA because it's not in the slides, it's not in the lab. I'm just including it as it's come up as we've been talking about it. So I'll leave it in here. Hopefully, it'll not have too much of an impact on the performance for the final element of the lab. But it'll be quite interesting to see anyway. So we'll leave it in. Once you've got these ILAs in there and such like, you can view them through the hardware. You can view them through the hardware manager. Now we've got this, we're going to dock this back into our Vivado overall. We're going to run the validation, and the validation should come up and tell us that there are no errors, critical warnings in this design, which is exactly what we want to see. And then, because we've captured this diagram here graphically in IP Integrator, we need to create a RTL wrapper for it. So what we're going to do is we're going to right-click on the block design here, and we're going to ask it to create a HDL wrapper. And we're going to let Vivado automatically manage that. So what that means is, as we change the wrapper, as we change what's in the design on the block diagram screen, the wrapper automatically gets updated for us. So we're going to click OK on that. It'll take a second to run through and do this. So this is a good question. So the ILA also includes its logic in the implementation. So yeah, so it's one of the interesting points about sort of implementing ILAs is that by putting an ILA in the design, you change the behavior. You can change the implementation, the floor planning, the behavior of the design, such that if you had an issue, you put the ILA in and then it goes away. You take the ILA out and the issue comes back. So you have to be very careful and considerate with how you go about putting the ILAs in, where you place them, and so on. And I'm sure there's more than one design floating about in production these days that's got an ILA in it because if it was taken out, it stopped working. Not one of mine, I would add, but I'm sure that happens. So as we've run through this, you'll see that the designs created the wrapper automatically. It's now automatically put assigned it to be the top level of the design as well. And you can see now we have the hierarchy under here for the tool. One thing I am going to do at this point is I'm going to open the constraints that we used in the previous project because the port names are all different and all incorrect, and obviously we've just changed that. I'm going to delete those and save it, and then I'm going to run synthesis again. So as we run through this, it shouldn't take a minute. Now, interestingly, here's what you'll see. It says up the top, it's running the multiple block runs. And if we go take a look at the design ones, what we'll see is we've now got these out of context modules being run in the tool. So you'll see that each one of these is being synthesized and created as its own design checkpoint. and then so you'll see it run the out of context design, and then once that out of context design is completed, you'll see it begin to run the overall synthesis. You can tell how the tool is from the fact that it has this little square next to it here. Tells you that it's going to do a out of context run. So once it's done the synthesize the modules themselves, it begins to synthesize the overall design at the top level there, which makes it really gives us really quick changes if we have to make anything, if we have to make any other changes. So yeah, this video will be available. It'll be, I think you can come back to this link and find it to watch it on demand. But what I normally do is I normally put it on my website as well, www.adiuvoengineering.com, with a link to it, and I'll upload it onto I'll upload the video onto YouTube and provide links to the slides and everything, so it's all in a nice central place. So as you can either watch it here or you can go watch it on the YouTube channel and get it. Now this design's implemented, so we're going to open the synthesized design in this case. And again, I'm going to just reassign the clock, the I/O. I'm going to assign the I/O this time. Find the scalar ports. Where's that gone? Scroll all the way across. Select those to 1.8. I'm going to find the clock. I'm going to put that on L16 again. And I'm going to use the I/O planning to auto place everything else. And I'm going to save it. So notice when we're saving it, because we're changing the constraints, we're gonna rerun and we're changing all this. So Jamie, that's a good question. I'm not going to touch on Tickle too much in this lab because it's a little bit more. It's more easier to show people the graphical side of it is than the Tickle side, I guess. However, if you go take a look, I don't know if you're aware, but I've done some classes with AVNet on the Ultra 96, the Mini Z, and the new ZU1 CG board, which will be coming out. And I'll put some links up to it later on. You can certainly find them on my webpage. There is a huge section in the, and those classes are free, by the way. There's free, they're free sort of free session classes looking at hardware, software, PED, Linux for each of those boards, like a one-day class that you can just sign up and do online for free. There's a huge section on using Tickle in those to recreate the designs and work with the design in Tickle there. So it might be worth, if that's something that's important to you, it's probably worth taking a look at there. Once we've got that, we should be able to come back and hopefully in our constraints file, you'll see that we've now got all the new constraints put in there. There's some constraints put in here down the bottom for the debug and the debug clock and everything, but we're not going to worry too much about that. We're just going to run through and run the implementation of our design. So Anil, how you do the debug or trace the signal is exactly how we would use it using the ILA design, just as I was showing. So let me just put this in here. So I've said my website a few times. I'll just put a link in here just so everybody can see it while that's building. And the course, the workshops. I will put a link into the workshops in here in a second, so as you can go find them. So Jamie, this should be the link to the training courses for the Ultra 96 and this one will be the Mini Z one as well. There will be a ZU1 CG course coming out there. We've literally just finished that, and the files are across being uploaded. So hopefully they'll be uploaded in the immediate future. But that'll give you quite a bit of information to hopefully get started with and go away with it. And thinking of like whatever else I would like to. So this year my plan is to do 4 of these like workshop webinars. So if anybody's got any ideas like what they would like them on, we've recently done HLS, we've done Pedal Linux, maybe some people, maybe scripting or something like that. If that's of interest to people, we could take a look at. I was thinking about doing one on verification, taking a little bit more of a look at sort of, writing simulations and formal coverage and things like that. So with this open, what we're going to do is we're going to open the design now. Open the implemented design. Yes, we'll close the synthesized design. Yeah, so if you have somebody was just asking, saying, I've got a Zyber, well, can they follow along? And yeah, of course they can, because it's a simple concept. So you just target the Zyber board if you've installed it, and you can work through and follow that. With this, you can see. Let's take a look. Let's pop this out for the time being. We can see our logic here, what's been implemented. We can see where all of the IO's been where all of the logic's been implemented. What do we have over here? We have that's a boundary scan element that we're using for that. There is actually a HLS one on my website. We did a HLS workshop just last year, the back end of last year. So let me put that on there now. In fact, there are actually 2. But this one, there is a webinar and a workshop. So there you go. That's the workshop one, which is the longer one. So here, looking at the implementation view, we can see where it's placed everything. It's placed all of our logic. If we want to, we can zoom in. I'm just going to pop this back in for the time being. But the one thing that we've forgotten, of course, is we've not done any timing constraints yet. We've not applied any timing constraints to this design. And you'll see, it says all specified user timing constraints are met. Yeah, exactly, because we didn't do any. So we're going to add some timing constraints in, and we're going to rerun it. So we're going to come here to tools. We're going to come to timing. We're going to go to constraints wizard. It's going to open us a simple element. We're going to come here. There's only 1 clock in this design. Yes, we can control the RTL mapping on the device. And I think we're running a little ahead of where I was thinking, because this machine's being so fast at building everything. So if we get to the end of it and we've got a little bit of time, I'll show you how to do that, because it can be really quite useful. So we're going to give this. I want this run to 200 megahertz. This is running in a Spartan in a 7 series device. So 200 megahertz. It should be able to do this quite easily. We're going to finish this, and then I'm going to ask. No, I'll not ask it to you. And we're going to finish that there. So somebody was just asking about going through the Mini Z training course on 2022.2. No, there wouldn't be. You might just have to upgrade. We provided all the solutions and everything. You might just have to work through those and pull those into and upgrade those. If you open the project in 2020.2, it'll ask you to upgrade it. If you upgrade it, it should be okay. I think, Gary, Pink. I'm a big fan of Pink. I think we'll definitely do something in Pink. So partial bitstream is quite interesting, Cameron, because partial bitstream allows you to just do a small section of the FPGA and to reconfigure a small section of it. And I'm beginning to sound a bit like a just somebody redirecting it, but I actually have. If you go to my website and go to white papers, I think. If you go here, there is actually a step-by-step guide on how to do partial reconfiguration there, and using the Vivado tool. So that'll if you're interested in doing that, but that'll help you. But that partial reconfiguration be really quite useful, because if you're looking at sort of like a signal processing chain or an image processing chain, and you just want to change a filter, you know, you can just reconfigure that element of the FPGA to change the filter performance or change the filter that you've got in there, and that can be really quite nice. So we've put a timing constraint in. It should be in our XDC file. If we go back into the sources now, if we go down somewhere, we will see this line here, which tells us our clock constraint. So it's got a period of 5 nanoseconds. It's a 50-50 clock, and it comes in on port clock 0. You'll notice by adding these constraints, by changing these constraints, we've gone out of our synthesis, and implementation is out of date. So I'm just going to rerun that again. Should have started rerunning this really while I was answering questions. I'll close the implemented design, just give it a little bit more memory to run through. So if you've got any questions, just sort of pop them through into the question, into the mark, and then we can see. Cameron, I think I also did some blogs on that, but I can't be sure. So it might just be worthwhile just doing a quick search on the blog page as well, because I might have done something. You have to be careful about some of the smaller devices. You can't do partial reconfiguration on, but I think you should be okay with most of them. So maybe I think everybody seems to like the idea of pink. Well, maybe we'll take a look at pink for like real world industrial sort of engineering use cases, because I think that's quite important. We've got several sort of customers that do that to accelerate their prototyping and so on. So it's running through the optimization of the design. The KV260, Cameron, is a great board. We have a couple of KV260s, we have a KR260, and we're just doing a couple of actually I saw Sharuk online earlier on. So we're doing a couple of board designs as well with some custom carrier cards for some really, really cool sort of proper industrial sort of electronics that harks back to my hometown and such like. So now we've run this through and we've got the implemented design again. We notice that we've got, it tells us here, implementation complete. Unfortunately, we've failed timing. So ATA really, the implementation time, like I said, you can do that recompilation, which I didn't actually turn on this. But this is quite a high-end build machine, so it's only going to get slower on sort of anything else, although screen sharing does save its time. The real key takeaway is simulation is your friend. Simulation is what you want to be doing to build things through and to get things working and to give yourself confidence that it's working. You don't really want to be just throwing things on the hardware and then running through it and trying to see what's going on, see whether it's working or not. Simulation is what's going to give you that nice sort of warm feeling that it's all going to be okay. So when we come into here now, we see that we have some failing endpoints. We have some failing timing constraints because we said we wanted to run at 200 megahertz, which it's not hugely fast, but it begins to be challenging. So we can take a look at our timing summary down here. We'll see that we've got intra-clock paths. And so what this means is that a path on clock 0 is failing. And if we take a look at this, we can see that we've got a setup violation. So we're arriving, we have a problem with the setup. And if we click on here, we can highlight it and we can zoom in a little as to what's going on. Maybe we can zoom into the area. Can we all see this okay? Might try and make it a little bit bigger so as we can see what's going on. And what you can see here is if I hold the mouse over it, you can see here we've got a RAM element, a RAM block element. So that's being used as part of the FIFO actually. And you can see the path. It's showing the registers here coming through here. So we've and the flow coming through here. So it's going through a lookup table here. It's going through some carry logic here. It's running through here through another lookup table, and then finally it gets to a register. But there's quite a long path from that register, from the output here to the register here at 5 nanoseconds. And you can see that if you look at the clock timing and the path here, we can ask it to show us the path. So if we take a look at the schematic, we can see, click that out there, we can see the exact path that's coming through here. So there's sort of 1, 2, 3, 4, 5 elements of combinatorial elements and a huge amount of routing before we get to that flip-flop. So it's not going to give us the timing performance that we want, and hence we have a failing constraint. So there's a couple of ways that we can fix this. The first way that we can go back to is do proper excuse me, is begin to do proper design and think about what we're going to do. Now, one of the rules of good design is that you should always try to register the outputs, because that gives you a nicer probability of, you're not going from a combinatorial output to the combinatorial input of your block to a register. You're going to go from a register through some combinatorial logic on your input to another register. So it's a good practice to do that. But Tan, I see your question, but I'm not quite sure what you mean by that. If you could expand on it, I'll try and answer it. So we have the FIFO generator. We can double click on the FIFO generator. And one of the things I did when I recreated the FIFO generator, if you can remember, is I specifically said we're going to keep the output registers turned off. And that was the reason that I wanted to create this issue. So if we turn the output registers on, we can leave them as embedded registers. We can put them as fabric registers, or we can have embedded and fabric registers. I think we'll be okay with the embedded registers. So I'm going to click on OK. And then I'm going to save the design. And then I'm going to run through and run the implementation through again. It's going to tell me everything's gone out of kilter. I'm going to run that through. Please, any questions, any thoughts, any comments? Just keep throwing them in the chat. So that's a great question. So an embedded register would mean, and I've closed the view now. An embedded register would mean an embedded register within the block RAM itself. So within the block RAM, and then there's a FIFO. A fabric register that could also be implemented if you wanted. So you could put the register in the user register in the programmable logic, user register in the block RAM, or if you wanted sort of belt and braces, you could use both. So, Atarius, it's a good question, a good point. So you're saying that inserting the register in a long path will increase resource utilization, and of course it will increase resource utilization. FPGAs are generally logic register rich anyway. But you could also try to replan the floor plan if you wanted to by hand to try to bring those gaps together to try to remove the delay. That would be also valid. It might take a little bit more time to do. In this instance, I'm just showing how to put the register, just showing that it's good practice really to register the outputs of every one of your blocks. So yeah, but yeah, you can. I understand now. Yeah, so you can turn on and off if you want to drive external FETs. The FPGA, everything that's happening in the FPGA is happening truly in parallel. So if you wanted to turn all of the I/O on and off at the same time, then you could. You might run into an issue called simultaneous switching outputs or ground bounds, but I doubt it in what you're trying to do. So yeah, you could literally have a port of 8, 9, 10, 16, 24 switching and going that way. You'll notice this time it's run through and it's telling me it's implemented, and it says implementation complete, and it doesn't say failed timing. So that's a really good thing there that we've managed to get through, and we've done it. We'll open the implemented design and take a look at it. So Gareth, I don't think you have to leave the register. I don't think you as the engineer have to compensate for the propagation delay through the block RAM. I think you can just do it for one clock and then it will flow through. It's just the latency on it coming. It's just the latency on it coming out. So as opposed to it being a 1 clock latency, it will be a 2 clock. It'll be 2 clocks after you've asserted that. So somebody's asked a great question. What is the suitable method when it comes to LUT generation, IP integrator or hard coding? Is it a good idea to mix both? Yes, is the answer to that. It really depends on what you're trying to do. You know, if you're trying to do a Zinc or an MPSoC or an ACAP or a microblaze solution, then you're definitely going to have some IP integrator. You're definitely going to have some IP integrator in there because it's the only way to design it efficiently and make it look and work. Some other elements, you know, if you're designing custom IP modules that you might write those in your own editor, say in VS Code, and simulate them and make them standalone blocks and then import them into Vivado. There's no sort of hard and fast rules on what to do. The best thing to do really is what's most suitable and sensible for your application. Because that's the important thing as an engineer is trying to work out the most sensible solution for the application to address the challenges that you face, and then to address it in a sensible manner. So you notice this time we have a worst case negative slack, which is positive, a worst case hold slack, which is positive. And if we look at our device now, let's see if we can find our block RAM. Shouldn't be too hard to find down here. You can see that we can find our block RAMs. We can see, let's go find that timing path again, actually. Debug. That address register. Let's take a look at those in the slightly different, but we can see that we've got this time, you know, we've got no timing issues at all. So the top 10 worst case timing issues that are being reported, the top 10 worst case paths, they're all still positive paths. They're all still passing, but it also always reports the top 10, and they're all associated with not unreasonably the debug element for the ILA that we put in. and then a few elements according to, in fact, they're all ILA related. They seem to be more all ILA related ones, which is good and what we would expect. So that's really nice. We've got a really nice timing closure at this point in time. We've run through, we've done the design. Oh, we've got it working. So we're a little bit ahead of time. So all I'm going to do is I'm going to close the implementation view here. I'm going to go off. We've finished the labs. They're all sort of finished. So I'm going to go through and show you a few of the things that we've talked about along the way as well, that we were going to do. And somebody mentioned about how you could control placement and where the placement goes. And one of the best ways to do this, we could probably break this now, is to open the synthesize design. Okay. And in the synthesize design, if we click on the design here, we have the net list. We have obviously we have the design one. We have the nets. We have the FIFO generator. We have the ILA, and we have the average. Yeah, I'll come back and talk about I'll actually give you an example. We'll run those reports and get what they and get those out of there, get those out of the tool as well. One other thing I'm going to do that I'm going to show you how we can, and this is going to break, should break this, I think. And what we're going to do, should break the timing maybe. What we're going to do is we're going to draw what's called a P block, which is a positioning block. And in this one, I'm going to draw a P block in here. And we'll call that P block 1. And let's draw another P block here. And we'll call that P block 2. So what we can do is, if we want to, we can drag across the elements such as the average block that we've written, and we could drop it in this P block. And we could drop across the FIFO, and we could drop the FIFO in here. Not really sure what this is going to do in terms of timing, but hey, it'll be quite interesting to see. We can save that. We can, yeah, well, that's okay. It's going to go out of date. So if you remember previously in our previous implementation, all of the logic was implemented around here. But now this time, what we've said is actually no, put the logic here and put the logic here. Well, put one element of the logic here. Put the average here. Put the FIFO here. And we can see this in our XDC constraints. If we reload those, we can see that we've got P blocks created here, and such like, and they've been added, and the relevant elements have been added to those P blocks. Let's do an implementation. Is there anything else apart from the rent value that we would like to come back to? So just to come back to that, to the rent value. So what the rent value is, it's what's called a rent exponent. And it's a relationship between the number of ports and cells of a particular netlist partition. So it uses that rent exponent it uses the number of ports that the design's got, the number of cells that the design's got, and then indicates, and the fan out. And then uses that to calculate the rent exponent. There must be more to it than that. It's not something I'm a huge expert on, I must admit. It comes from. It's quite a famous rule called Rent's rule. So I'll stick it in. You might be interested to read that a little bit as well, which will show that. So let's open the implemented design. Now that that's run, we'll close the synthesized design. I'm quite impressed this still actually passed timing, which shows the important point to everybody of making sure all your outputs are always registered. You can see this time now we've got the, in fact, let's color them. So we can see this time if we close that, go down here, let's highlight these purple, and let's highlight these. And you can see now the tools run through, and it's implemented the design exactly as we said it should do. You know, we've got the average, I think, that we assigned to P block 1, and that's all in this region here. We've got the FIFO generator in this region here, and then all of this down here will be associated. Let's go and prove this. All of this will be associated with the ILA, I would imagine. So yeah, so we have all of this associated with the ILA. So we can see that by using these P blocks, we've been able to control where we want to place things in the design. And if you're designing things like cryptos or, you know, like high reliability, high integrity systems, you can use these in line with what's called the Vivado isolation verifier to actually create functions and isolate functions away from each other, and then prove that those functions don't interact with each other, which is really useful for timing closure, which is really useful for not only for safety critical stuff and for timing closure. So for large scale debugging, I would say, and actually it's one of the things that I'm gonna be blogging about in the next few weeks, is that Vivado simulator has the ability to do functional coverage. So it has the ability to do functional coverage using system Verilog. Excuse me, using system Verilog assertions. So I would, when possible, I would try to use standard simple things of simulation, functional coverage via assertion-based verification, and then for those things that come up that are slightly difficult, you know, because it always, with the best way in the world, no matter how well you simulate something, issues always come up. There are always challenges, and perhaps you're talking to a processor or an external board and things don't quite work so well. That's a good point to start looking at doing sort of ILAs and debugging the design on the hardware. I would say try to do as much as possible in your verification environment, because we all simulate, right? Everybody does simulate. Everybody always uses simulation to do that. So let's ask let's have a quick poll. Who does simulation? Do you do simulation on your designs? So it's always good to be able to do, you know, to simulate our designs and see what's going off. I thought the options there were quite good, so it's quite a good one. So is there anything else that we want to talk about or ask any questions on as we go through this? Because this has been quite a whistle stop tour of Vivado. I'll tell you what, let's run a few of these reports out of here. So let's just go over here, because we've run all the way through. So let's take a look at here. We can do reports. And let's do in fact, actually, no, let's yeah, let's do the design analysis report. So we can do the design analysis report. I'm not going to ask it for a huge amount of complexity here. You know, I'm just going to ask it to go through all the timing paths. Let's ask it to do min and max. We'll ask it to look at complexity. We'll ask it to look for congestion. And we'll ask it to open in a new tab. We'll let it run through. Once that's run through, we'll pop that out as a design analysis. Pop that out and then maximize it. So you can see it'll run through, and it'll run through and give us the general information on what it's done. It'll give us the setup and hold path. So it'll tell us about clock relationships, clock groups, you know, the logic levels, and the clock uncertainty. Oh, that's a good question. I'll come back to that one in a second. Then we can take a look at the complexity as well. So the complexity characteristics. So again, we get that, you know, we get the average fan out of our design, and understanding and controlling this, you know, thinking about this is really, really key. One of the key elements of being a good FPGA engineer is not just sitting there throwing out like VHDL or Verilog, but it's actually thinking about what your design is going to, what that VHDL and Verilog is going to turn into and what it's going to synthesize as, so as you can try to control the fan outs, the amount of logic that's in between clocks and such like, so as you can get better implementation performance on your device and spend less time cycling round and trying to work out what the issue is. So we can see we've got some nice complexity characteristics there. We have some congestion reports, but there's no congestion because there was nothing above sort of five levels. Let's take a look at running the quality of results suggestion. Ask it to report all suggestions. And once we've got that, we'll see it comes through and it tells us whether it can, what it can do in terms of suggestions for our project and what it should do. You'll notice it's making, this is past timing, but it's still making suggestions. It's telling us whether we can whether it can be applied automatically or not to the project. It's telling us whether it's incremental place and route compilation friendly or not. So if we want to, you know, we can write these suggestions to the project, and they'll be included the next time round we rerun round and do the build. If you click through here, you'll see much more detailed information on the logic information and on the netlist. So it's a very good. These things are very good to do, and obviously I've shown these at the end after we've worked through the labs to see them. But if you're starting out a new project, you're starting out with simulation synthesis, then they're a good point to do. Just wondering if I have a more recent complex project that we could open and run a design. We could run a design on. Let's have a quick look. Maybe we could take a look at the ZMod one. Yeah, let's see if we can open. Let's open this one. Project. So I'm not sure. Somebody's asked a question about ILA to Python parsing. I'm not sure what you mean by that, but it's possible to sort of grab data up over the using up over the ILAs and such like, and dump that out such that you could run through it and parse it with Python. Is that what you had in mind, or were you thinking more of a pink-based infrastructure where you've got ILAs in them? So let's take a look at this design. This design is a little bit more complicated, I'm hoping. So in this design, we've got two Z mods that are back to back. This is a Hackster project I did recently, actually. So there's no processing system in it. It's just a digitizer, an arbitrary waveform generator, and a high-speed A to D, and they're connected together each other, and they're connected through a FIR compiler, so a FIR filter is going through as an AXI. Stream. Now there's a couple of different clocks in here. They're all kind of related to each other. The right bit stream is completed, so we should be able to go in here and do report. If I could type report CDC. Fatal thing. You have to open. You have to have at least the synthesized design actually open. Yes, it is available on Hackster. I'll put the link in here. There you go. If you've not seen it, I'll pull it across. This is the not currently signed into it. But this is the project that we're talking about, which teaches you how to do digital filters using this thing. It tells you all about the theory of digital filters, how to calculate the FIR coefficients, how to set up the design with the Z mods, and then somewhere down the bottom. Cool, this was a long project. Somewhere down the bottom, we show you the hardware setup with the Eclipse with the Z mods connected to each other back to back, connected to the analog discovery, and then we'll show you how to generate the filter coefficients, and then take a look at the FFTs of the filter coefficients as we move information through the pass band, the stop band, the high pass, the low pass, and band stop. And we show you all, we show how to simulate it and see what it looks like in the ILAs as well, so as you can see everything. If I'd have thought about it, I would have set that up such that I could have it running to demo it during this lab. So let's try here. If we do report CDC, we get a CDC report in our design, which shows us that it's all nice and safely timed, or that we've got false paths in there as well. Tells us that we've got one in here with no primary clocks, which has got some unsafe in there. So I guess I'd better go and look into that. We can also get a clock into action report out, which will be quite interesting to take a look at. Let's do a report. Clock into action. There is some little thing I can never remember to make it do it. Let's just do report clock into action. So we can see this in a textual based clock interaction table here. What I want to see is that nice graphical one that I showed in the slides. So we'll do the always thing, we'll put the dash help. I think we just have to give it a name. And then we get this nice clock interaction report, which shows the interaction between the clocks and whether there is a safe or an unsafe path between them, whether it's timed, whether it's untimed, or whether there is a no path, or whether there is something that is timed that is unsafe. But I don't think there is any. I think that's probably an exception that we could raise an exception on and say that that is okay. So is there any other questions before we wrap up? We've had a bit of a whistle-stop tour around Vivado today, you know, so we've looked at how it is, what it works like. We've looked at a simple way to create a project. We've looked at the design analysis reports, the quality of suggestions reports. We've looked at how we can work with IP Integrator, how we can add in an ILA, how we can find and correct timing issues. And then, of course, we've gone a little bit further because we've got a little bit more time. So we've gone away and looked at what we could do with creating things like P blocks. We've taken a little bit more of a look at the event analysis. And we've then gone and opened up a little bit more of an in-detail project and run the reports. In fact, let me run the reports for this one to see what it actually says. Let's run that one. Let's run the design analysis report. There's no congestion on that. Quality of results report. It tells me, see, it tells you the overall assessment, that there's a small chance of success. It was successful. But it tells me that I do need to do some, we do need to look at the timing constraints on it and sort the timing constraints out a little bit more. But you can run through that and see the issues and see what it says. If we run the suggestions, what does it suggest? Let's write those suggestions to the project. And we'll see what we can do with it. So somebody's just asked some tips for entry level engineers and what to look out for. And thank you very much for saying the nice thing about the tools. You know, I've been using these for Vivado for sort of 10 plus years, I guess ish now, maybe 10 years. Yeah, coming up on 10 years now. So I guess I'm fairly confident with it. I guess my tips for sort of new entry level engineers are, one thing is really to sort of read the manual and try to understand what you're trying to do and how you're trying to do it. The other thing would be to verify and simulate as much as you possibly can up front. You know, you should write a module and simulate. You know, if you're using IP Integrator, then use some of the things such as the Xilinx AXI verification IP to help you verify those blocks and those interfaces, because it's easy to get tempted to just want to build something and drop it in hardware and see what happens. But when that goes, if it works, hey, brilliant, it works. You know, it's when it goes wrong though that becomes very difficult to go away and find and work out what's going off. And the other thing I would say is ask questions. You know, ask questions of the other engineers around you. You know, when they're doing things such as, you know, why are they doing something? What did they, you know, what's the reasoning behind it? How does it help them? And try and ask questions and learn as much as you can from those engineers. You know, we were all young engineers once, and I'd like to think that we'd all help young engineers learn and have such a great career as we've all had. So I think that's quite important to do. So if there's any last questions, I'll try and answer them. If not, we can wrap up a minute or two early. I hope it's been useful to everybody. I hope everybody's learned something today and thought, this was well worth coming. If you've got anything else to think about, any other workshops, tutorials, classes, things that we should be looking out for, then it will be. Yeah, Austin, yeah, it will be. Keep an eye on my website, although you should be able to come back to this web page, the Livestone page, and you should be able to see it as a recording, and you'll be able to watch it. I'll throw it on our YouTube channel as well, so that I can include links to the GitHub and everything. So the links that we had today are this one here. Timing requirements. That's a good idea, actually. I will put that. I will put that in there, because timing requirements are quite interesting, because it's not only internally to the device that we have to think about. We have to think about the externals of the device as well. Let me find the YouTube channel for Adiuvo. And then I think that's it. I think that's our YouTube channel. I have the great question there about what resources you recommend, and I've been throwing out a few blogs recently on resources and things that I think that are useful when you're starting out as engineers. So if you bear with me 1 second, I'll put them up. I'll put you some links in. So this is the one. This is the one that's sort of like looking at development boards that are useful, that are interesting to get started with. This is the one with some useful books, and not everything on there. So you've got to pay for. Obviously, I've tried to keep it nice and straightforward. And then this is the one that went out this week that looks at a few additional things that you might want to think about when you're a little bit more into it. So taking a look at things like simulators and editors, and what editors we want to start building. And there's a whole host of FPGA resources out there. Yeah, there is, Austin. There should be links. That was the one we did one last year on Linux. And somebody's asking that ChatGPT to write something else. Of course, I tried that. I tried that in a blog a few weeks ago. I wasn't too worried that I was going to have to get a real job yet, not being an engineer. Take a look here. You can see that there. Interesting. Somebody was asking about. I did a project on Axe to use DC to do DC remote control. I used a microplace. That's a good question, actually. Probably because I have a love of microplace. Let's just take a look at that project. Well, I think I did use some. Oh no, I got captured. I think I did use a PWM in there that I put in the FPGA. I think I wrote an FPGA PWM. But I controlled it over a microplace. That was what I did. Yeah, I wrote the PWM and everything in there, but then I wanted to control it over a UART, so it was quicker and easier to just write it as using a microplace than it was to write some RTL to bring in the UART to do the control, and that was all really. And security, I'll have a think about security on the FPGA platform. It's obviously it's a critical thing that's very important. Maybe maybe we do that as a workshop or something like that, just to get everybody aware of what's going off and what you can do, and you know, anti-tamper and things like that. So if there's any final questions, if not, thank you very much for coming and spending a couple of hours with me as I talked about Vivado and AMD FPGAs. Yeah, so Kenny, yeah, all the workshops and everything, it's on YouTube, or you can find it from my website, which again is here. Link checks is an interesting one. Possibly Austin. Yeah, maybe. Yes. Yeah, probably. Right. Thank you very much, everybody, for this, for attending and for learning about Vivado. And we will talk again soon. Let me end the event now. Thank you very much. Bye-bye. Stay safe and healthy, everybody. Thank you. Bye.